The first goal of today is to sketch a proof of this theorem, which says that the four models of the hyperbolic space I presented last time are mutually isometric. Some of you could ask the following question: are we sure that H and R is a Riemannian manifold? It's not clear from the definition, because the metric on this model is G-1R equal I star Q bar, where I is the inclusion of H and R in R n comma 1, and Q bar is the pseudo metric known as Minkowski metric, given by this formula. The problem is that here there is a minus sign, so it's not clear at all that this is a Riemannian metric. We could prove that the answer to this question is true using result from the theory of some manifolds of pseudo-Riemannian manifolds, but I decided not to present this theory in this course. But this is not a problem. Actually, this is a consequence of the following fact: there exists let's say isometries, the following isometries. C between H and R and K and R, pi between H and R and B and R, and K from P and R and U and R. If, for example, you prove that there exists an isometry between HNR and KNR, or you prove that there exists an isometry between HNR and BNR, as a consequence you get that the answer to this question is yes, because it's clear that KNR and BNR are Riemannian manifolds. Consequently, if you look at definition of isometry, you conclude immediately that this is a Riemannian metric. What I'm saying will be clear in a few minutes. Let's see how to construct the isometry denoted by C. So this is what we call central projection, and it is defined this way. I need to make a picture. So suppose that we work in with n equal 2. So I can make a picture precisely. This is tau, this is xc1, and this is xc2. This will be the point of coordinates 0, 0, r, and this is the upper sheet of the hyperboloid. Then you have to consider, let's use another color, a disk of radius r located on the plane of equation tau equal r. This is the disk which is the underlying set we used for defining K and R. And now we will construct the map C as follows. Suppose that P is a point on this hyperboloid having coordinates C1, C2, Cn tau. Then we consider the straight line joining this point to the origin, and we associate to P the point W given by the intersection of this straight line with this open ball. So suppose that we want to write down the coordinates of W. They are given by W1, W2, Wn, R. And some relatively simple computations shows that C of xc tau, where xc denotes xc1, xc2, xn, this is equal to r c over tau. It is possible to prove that the length of c tau square is equal to r square 1 minus r square over tau square, and this is more than r square. So this says that c tau belongs to Kn R. We want to prove that this map is a diffeomorphism, Clearly, this is a smooth map. Tau cannot take the zero value because we are assuming that P is a point of this hyperboloid. Consequently, the value of tau are greater or equal to r. This is a point of coordinate 0, 0, r. And what is the inverse? It is possible to prove that if you call W, W1, W2, Wn, the first n coordinates of W, you have that C inverse of W is given by Rw over square root of R square minus length of W square, R square over square root of R square minus W length of W square. Also in this case we get easily that this is a diffeomorphism. Why? Because we are working on the open ball of radius r, so the denominator never vanishes. It remains to prove that it is an isometry. So C is an isometry between G-1R and G-2R. This was the metric on H and R, and this was a metric on K and R. In order to prove this, we actually work with the inverse. Because it's easier from the computational point of view. And we have to check that C minus 1 star of G-1R is equal to G-2R. This is easier to do than showing C star G2R, G-2R equal G-1R because of the expression of G-1R. We use in fact the fact that G-1R is I star Q bar, which has a relatively simple formula, and it is clear that if we call C the first n components functions in the formula for C inverse, and the last one will be called by tau, then C inverse star G dash 1R is just the sum of dxi I square minus d tau square. So there is a computation to do. You use the formula for C inverse I wrote down on the blackboard, and you use the fact that dxi is r d omega, sorry, dwi over square root of r square minus w square plus rwi sum on j wj dwj divided by r square minus w square 3 over 2. And d tau, this is r square sum on j wj dwj divided by r square minus length of w square power 3 over 2. And this implies that C inverse star, I write it again, G dash 1R is a G dash 2R. Now what about the isometry between H and R and B and R? Pi is what we call hyperbolic stereographic projection, and it is defined as follows. Let's make one more picture. So suppose that this is a point of coordinate 0, 0, R. This is the upper sheet of the hyperboloid. This is the point of coordinates 0, 0 minus R, and this is the lower sheet of the hyperboloid. Then this time we look at the plane tau equals 0, and we consider a disk of radius r on it. So if P is a point of the upper sheet of the hyperboloid, so P has coordinates C1, C2, Cn tau, we consider the straight line joining P to this point here, and we send P to the point U, which is the intersection of this straight line with the plane of equation tau equals 0. So we write this way, and this belongs to B and R. if exactly as before the first 10 coordinates are represented by c, then you can prove that pi of c tau, this is equal to r c divided by r plus tau. And if you call u1, u2, un the coordinates, the first coordinates of u, then u, that is the first 10 coordinates, is given by arc c divided by r plus tau. And you can prove that this one is r square tau square minus r square tau square plus r square, which is more than r square. And you can prove that the inverse as the following formula. Both of pi and pi inverse are smooth maps. It is clear that r plus tau never vanishes, and it is clear that the denominator r square minus u length of u square never vanishes, because we work with the open ball of radius r. So we got that pi is a diffeomorphism. It remains to prove that it is an isometry. So pi is an isometry between G'1R and G'3R, and the technique we use is exactly the same as the one we used before. It is convenient to work with pi inverse. Because the metric G'1 is a simpler expression, and in order to prove that this statement is true, it's enough to check that pi inverse star of G'1R is G'3R, and this is done exactly as before. If you use the notation C tau equal pi inverse u, so precisely this is C, and this is tau. Then pi inverse star g dash 1r. This is the sum of d xi square minus d tau square, and using the formulas d xi equal 2r square ui over r square minus length of u square. Differential of this, and d tau differential of this function. You can prove that this is true. Sorry, let's write that this is g dash 3r. Now the last isometry, k, between the u and r, the upper half space model, Poincaré half space model, and the Poincaré ball model. We consider first the case where the dimension is 2. In this case, if we write the coordinates on the ball as u v, and the coordinates on the half space by x, y, and we pass to the complex notation that is w equal u plus iv, z equal x plus iw, x plus iy. Then kz is given by ir multiply this rational function, which is a variant of Cayley transform. It is possible to go back to the real notation, that is to separate the real and the imaginary parts of of W. Of course, this is W. And we have k of x, y equal 2r square x divided by length of x square plus y plus r square r times and the same formula holds true if we work in the higher dimensional case. That is the case when x means x1, x2, xn minus 1. The formula for the inverse, if we write this as uv, is given by k inverse of uv equals 2r square u divided by length of u square plus v minus r square, r multiplied by r square minus length of u square minus v square divided by length of u square plus v minus r square. In this case, the computations are more complicated, as you see, and what we did so far is that we proved that K is a diffeomorphism. It is more complicated to prove that we have an isometry. So it holds true that K is an isometry. That is K star G'3 R is equal to G'4 R. And this is the end of the theorem, the end of the proof of the theorem. So a word about the notation. We have seen that there are 4 symbols but in general the notation which is more used is this one, even though we are working with the other 3 models. And let's consider the following special cases. If R is 1, then we just use the expression hyperbolic space, and the notation is this: Hn Gcache, where Gcache, of course, is the metric you are using with a 1. So you can choose any of the models you have. You replace r equal 1 and you call the Riemannian manifold you get simply hyperbolic space, keeping using this notation here. Instead, if n is 2, then we have the name hyperbolic plane. An easy consequence of the computations we made is the fact that each hyperbolic space is locally, conformally flat. In order to prove that this is true, it is convenient to work with this model here or this model here. Why? Because if you look at the corresponding metrics, G-Chesh 3R and G-Chesh 4R, they are given by a function, a positive function, times a metric which is Euclidean. In the case of G3R, we have f times the Euclidean metric on the ball of radius r, instead if you work with G-Chesh 4R, this is f times Euclidean metric on the upper half space. Consequently, if you want to prove that there exists a conformal equivalence between the hyperbolic space and an open set of the Euclidean space, just use the identity map. So the conformal equivalence is given by the identity. Consequently, the pullback by this map of the metric is given by a positive function times the Euclidean metric. Now let's briefly discuss the symmetries of the hyperbolic spaces. It is possible to prove that if we denote by O n comma 1 the group of linear maps from Rn comma 1 to itself, that preserve the Minkowski metric, we get the isometries of this space, considering I want to tell you that this is known as n plus 1 dimensional Lorentzian group, and the group of symmetries of the group of isometries of HNR is obtained by this one. It is denoted by O plus and 1. This is the subgroup of O n comma 1, which maps the tau greater than 0 component of the hyperboloid to itself. It is possible to prove that O plus and 1 preserves H and R this means that it preserves Q bar. This is the Minkowski metric. This is true because by definition O n comma 1 preserves the Minkowski metric, and it isometrically, it acts isometrically on H and R. And it is possible to prove that this is the full isometry group, but we will not see the details of this fact. Then, using the same strategy of the proof of the fact that O n plus 1 acts transitively on O S n R, you can prove that O plus n comma 1 acts transitively on O H n R, where this is the set of all orthonormal spaces for the tangent space to the hyperbolic space. So I will leave the details of the proof to you. I would like now to change topic, and I want to start to talk about connections. Roughly speaking, a connection is a way of differentiating sections of vector bundles. We will use it in the special case where the vector bundle is the tangent space to a Riemannian manifold. So I say a connection is a way of differentiating sections of vector bundles that is vector fields. The reason why we need this machinery will be clear when we will introduce the notion of geodesics. So let's start with the definition of Koszul connection, or simply connection. So let pi be a smooth vector bundle over a smooth manifold M with boundary or without boundary. We use this symbol for the space of smooth sections of E, then a connection in E is a map denoted by this symbol that you can read as a nabla, or, well, going from the product of Km and gamma E with values in gamma E. It is written this way, so x, y is a pair which is sent on nabla yx. This is called covariant derivative of y in the direction of x, and it must satisfy the following properties. One, nabla yx is linear in x over C infinity m. This means that for any f1, f2 in C infinity m, for any x1, x2 in K of n, then nabla of y in the direction of f1 x1 plus f2 x2, this must be equal to f1 nabla y x1 plus f2 nabla y x2. 2, nabla xy is linear in y over r. This means that for any a1, a2 in r, for any y1, y2 in gamma e, we have that nabla of a1 y1 plus a2 y2 this must be equal to a1 nabla y1x plus a2 nabla y2x. And the last property is the following. For any f in C infinity m, then nabla of fy along x is given by f nabla yx plus xf y. Let's start proving some properties of the connection. The first one is its locality. The connection has been defined by its action on global sections, but as this lemma shows, it is actually a local operator. So for every x in K of m and y in gamma e, and P in M. This covariant derivative here at P depends only on the values of x and y in an arbitrarily small neighborhood of P that is if x equal x tilde and y equal y tilde in a neighborhood of P, then you have this identity how to prove this. Let's prove that the statement is true for the entry y. So bilinearity it is enough to prove that if y is 0 in a neighborhood, then nabla yx restricted to P, this is 0. Why this is enough? Because you can use this fact if y and y tilde coincide in a neighborhood of P, then you can look at y minus y tilde. This is a 0 in a neighborhood of P, and you can call it y. Okay, so choose a bump function phi supported in U, which is exactly this neighborhood here, such that phi P is equal to 1. this implies that phi times y is identically 0 on M. Why? Because if this is U, we have that y is 0 here, and phi is 0 outside U. So the product is 0 everywhere. Consequently, nabla x of phi y can be written as nabla of 0 phi y along x, and this is 0 nabla phi y x, and this is 0. So this follows from the linearity. Now we use the product rule. So now we know that nabla phi y along x is 0, but by the product rule, this is phi nabla yx plus x phi y. Now if we take into account that y is 0 on the support of phi, this implies that x phi y is 0, and this says that at P, phi nabla x y, this is equal to nabla x y at P, because phi at P is equal 1. So we got that nabla x y at P is 0. Now we prove the statement for the entry x. So suppose that the x vanishes in a neighborhood U of P. I have to prove that the covariant derivative nabla yx at P is 0. Suppose that phi is exactly the same bump function we used before. Then I have that phi x is identically 0. Then nabla phi x y can be written as nabla y 0 phi x, which is 0 nabla phi x y, and this is 0. So we prove that 0 is a nabla phi x y. Now let's evaluate this at P. This is phi at P nabla x y at P. Sorry, I have to use this notation. but this is 1, so this is nabla x, y at p. And this is the end of the proof. The next result I want to prove is a proposition which says the following. For every open subset U of M, there is a unique connection denoted by this symbol on the restriction of the bundle E to U, such that for any x in K of M and y in gamma E, we have that this is equal to the restriction of this covariant derivative to U. Proof. Let's start by the uniqueness. Suppose that you have such a connection and the x is an element of K of U and y is in gamma E restricted to U, then given P in U, use a bump function to construct x tilde in K of M and y tilde in gamma E, such that the restriction of x tilde to U is x and the restriction of y tilde to U is y. Where U is a neighborhood of P, of course. Then previous lemma implies that nabla y x U at P This is just this evaluated at P. But this connection here, by the statement of the proposition, that is nabla u x u y u equal this, it is equal to nabla x tilde y tilde evaluated at P. So observe now what we have here. This is something which depends only on nabla, and this means that if nabla u exists, then it is completely determined by nabla. So it is unique. And the formula is on the blackboard. This one is equal to this one. Now we have to prove the existence. So given x in key of u and y in gamma e restricted to u, for every p in u, we construct x tilde and y tilde as before. Then the idea is to define nabla u y along x at p using the formula I proved before. So I write this way. This formula does not depend on the choices of x tilde and y tilde by the lemma I proved before, because the value of this covariant derivative depends only on the values of x tilde and y tilde in a neighborhood of P, and they coincide with x and y. It is now necessary that we prove it is smooth, but this is clear because this covariant derivative can be defined by the same formula for any p in a neighborhood of a given point, and you have to prove it is a connection, and this is a lengthy computation, so you have to show linearity and that the product rule is satisfied. Essentially, linearity and the fact that product rule is satisfied follows from the fact that nabla is a connection. How much time I have? Okay, the last result I want to prove is the following. The value at P of this covariant derivative depends only on the values of y in a neighborhood of P and on the value of x at P. The interesting piece of information provided by this proposition is contained in the second part. We already know that this covariant derivative depends only on the values of y in a neighborhood of P. What is interesting is this part here. So how to prove it? By linearity, I can assume that x at P is 0. And what I have to prove? I have to prove that this is 0. Okay, so suppose that U is a coordinate neighborhood of P, and this allows us to write x as a sum on I of xi di with xi at P equals 0. Now I use a previous proposition, which says that I can work with this connection here instead of this one. Then for every y in gamma E restricted to U, we have that nabla uxy at P, this is nabla xi delta I of y at P, and this bilinearity is given by xi at P nabla delta I y at P. But this is 0, consequently this is 0. The consequence of this proposition here is that it makes sense to write nabla y of V with V in TPM How to evaluate this? Consider x in E of u, where u is a neighborhood, of P, such that x at P is V. Then nabla y V is just nabla y x at P. Okay, this is a good point where to stop. Thank you for your attention.